So now let's prove that given m convex functions gi of x, then the set omega formed as the set of points x such that every one of those functions gi of x is less than or equal to 0. And that set is convex. And the proof starts by looking at the simplest case where there's only one of these. Right, so for each I is 1 up to m, let's consider the set omega I being the set of x such that the ith function is less than or equal to 0. And that's it. Alright, let's prove that's convex. How do we do that? Well, we let 2 points be in the set, and this is to hold for every such pair of points in the set, and consider the line segment between these, and if that line segment between it is in the set, then omega I has to be convex. And we consider that line segment by considering all points z of the form tx plus 1 minus ty for t in the interval 0, 1. We need to show that z is always in the set omega I. Right, now how do we do that? Well, we find out what gi of z is. So gi of z, that's gi of tx plus 1 minus ty. And remember now that gi is a convex function. And remember the definition of the convex function says whenever you see gi of this particular combination, we know that that has to be less than or equal to t times gi of x plus 1 minus t times gi of y. And the beauty about this form is that t is between 0 and 1 because it's only the line segment we're interested in. So t is bigger than 0, bigger than or equal to. 1 minus t is bigger than or equal to 0. The point x is in omega I, so gi of x is less than or equal to 0. Point y is in omega I, so gi of y is less than or equal to 0. Which means this right-hand side is a positive times a negative, which is negative, less than or equal to 0. Positive times a negative, so that's negative. Sum the two negatives, it has to be less than or equal to 0 for this point z on the line segment, and so z has to be in omega I. And because that's true for all t in 0, 1 and all x and y in omega I, that says omega I is convex. Now recall one of the fundamental properties of convex sets is the intersection of any number of convex sets is also convex. So now let's look at the intersection of omega 1, omega 2, all the way up to omega n. Because all these are convex, their intersections has to be convex. So this is convex. But now what is this set? This set is the set of points x for which g1 is less than or equal to 0, and g2 is less than or equal to 0, and g3 is less than or equal to 0, all the way up to and gm is less than or equal to 0, which is precisely the set omega. And hence omega is necessarily convex.